Hi everyone, I'm Whit Roy. Today I've invited an electrical tutor and an apprentice to have a conversation as they go through topics from the EWRB Electrician Theory exam. I hope you enjoy this style of learning.
Okay, Sarah, let's start this session by saying what Topic 22 is really about. We're looking at three-phase motors, how they're built, how they work, and what can go wrong if things aren't right.
Yeah, motors always feel a bit more intense than house wiring.
That's totally normal. In domestic work, loads are mostly small and predictable. Motors are different. They draw high current, they heat up, and they react badly to faults.
Right, so more consequences.
Exactly. So we'll go slowly and connect it back to things you already know.
Okay, that helps.
Let's begin with the basic construction. Every three-phase motor has three main parts: the rotor, the stator windings, and the iron circuit.
Rotor spins, stator stays still.
Yep, that's a solid start already. Now there are two common rotor types. The one you'll see most often is the squirrel cage rotor.
That's the simple one, right?
Yes, think of it like a sealed unit. Aluminium or copper bars along the rotor, shorted together at each end with end rings.
No brushes, no slip rings.
Exactly. And because there are no moving electrical contacts, they're very tough. That's why they're everywhere in workshops and factories.
Less maintenance.
Yes. Now the other type is the wound rotor, sometimes called a slip ring rotor.
That's the one with brushes.
Correct. The rotor has windings connected to slip rings, and external resistors can be added during starting.
So more control, but more things to fail.
Exactly right. They're used where you need high starting torque like heavy machinery, but they cost more and need more maintenance.
So most of the time, we deal with squirrel cage motors.
Yes, especially at your level, that's what exams focus on most.
Okay, that makes sense.
Now let's move to the stator windings. The stator is fixed, and it contains three sets of windings.
One for each phase.
Correct, and those windings are spaced 120 degrees apart.
That spacing is important, right?
Very important. That spacing allows the magnetic field to rotate smoothly when we apply a three-phase supply.
So the rotation starts there, not in the rotor.
Exactly. That's a key idea. The rotor only follows the rotating magnetic field. It doesn't create it first.
Okay, field first, then rotor follows.
Perfect. Now those stator windings are placed in slots in the iron core and insulated to protect them from heat, vibration, and moisture.
So insulation failure is a big issue.
Yes, heat is the main enemy of motors. Once insulation breaks down, faults follow quickly.
That sounds expensive.
It usually is. Now the iron circuit itself is made from thin laminated steel sheets.
That's to reduce eddy currents.
Exactly. Laminations reduce heating losses and improve efficiency.
So the iron circuit is kind of the backbone.
That's a good way to think about it. Without it, the magnetic field would be weak and the motor would produce almost no torque.
Okay.
Now let's talk about motor frames and ventilation. This is important where motors are installed.
Because of dust and moisture?
Yes, the most basic type is open drip proof, or ODP.
That's for clean indoor areas.
Correct. Air can flow through, but they don't like dust or water. More common in industry is TEFC, totally enclosed fan cooled.
That's the one with an external fan.
Yes, no open vents, much better for workshops and plant rooms.
What about no fan at all?
That's TENV, totally enclosed, non-ventilated, used in quiet or clean environments.
And explosion-proof motors?
Those are for hazardous areas, fuel depots, chemical plants, dusty environments, built to contain internal explosions.
So wrong motor in the wrong place equals danger.
Exactly. Selection matters.
Okay.
Now let's move into how the motor actually works. This is the part many people find tricky.
Yeah, this is where I get lost sometimes.
That's okay. Let's slow it down. When a three-phase supply feeds the stator windings, three currents flow, each 120 degrees apart.
That creates a rotating magnetic field.
Yes, smooth, continuous rotation. That rotating field cuts across the rotor conductors.
And that induces current in the rotor.
Exactly. Faraday's law at work. That rotor current creates its own magnetic field.
So now there are two fields.
Yes, and the interaction between those fields produces torque.
So torque only exists because of that interaction.
Correct. Now, here's a key exam point. The rotor can never reach synchronous speed.
Because then there would be no relative motion.
Exactly. No relative motion means no induced current, no torque.
So slip has to exist.
Yes, slip is essential. Slip is simply the difference between synchronous speed and rotor speed.
Ns minus Nr.
Correct. And synchronous speed depends on frequency and number of poles.
Ns equals 120 times frequency divided by poles.
Perfect. Now at full load, the motor runs slightly below synchronous speed.
That's full load speed.
Yes. Now imagine the torque speed curve. At synchronous speed, torque is zero.
Because slip is zero.
Exactly. As slip increases, torque increases until it reaches breakdown torque.
And after that, torque drops.
Yes, if the motor slows too much, it can stall.
That's bad.
Very bad. Now let's talk about voltage effects. What happens if supply voltage drops?
Less magnetic flux?
Yes, and to produce the same torque, the motor draws more current.
So more heat.
Exactly. Low voltage causes high current and overheating.
So low voltage isn't safer.
Correct. That's a common misunderstanding.
What about losing one phase?
Good question. In star connection, the motor usually can't start at all.
And in delta?
It may keep running, but current becomes unbalanced
So overheating again?
very quickly. That's why phase failure protection is important in industry.
I don't see that much in houses.
Exactly. That's why this topic feels unfamiliar.
Okay.
Another common fault is winding reversal. If one stator winding is reversed, the rotating magnetic field collapses.
So the motor might hum but not turn.
Yes, high current, vibration, overheating.
So wiring mistakes matter a lot.
They do. Now let's talk about power factor and efficiency.
Motors are worse at light load, right?
Correct. At late load, power factor is poor and efficiency is low.
As load increases, both improve.
Yes, up to rated load. Motors work best near their design point.
So running oversized motors wastes energy.
Exactly. Now about starting current.
That's much higher than run current.
Yes, typically 5 to 8 times full load current.
That explains why starters are needed.
Exactly. Star-delta starters reduce starting current.
By starting in star, then switching to delta.
Correct. And direction of rotation?
Swap any two phases.
Perfect. That reverses the rotating magnetic field.
Okay, this is starting to fit together.
Good. That's the goal. Not memorizing. Understanding.
Yeah, it feels less scary now.
That's how it should feel. Motors demand respect, not fear.
Thanks, Mark. This really helped.
No worries. Now we're talking about motor starters and what they actually do beyond just turning a motor on and off.
Yeah, I always thought a starter was basically just a switch.
That's very common, so you're not alone there. But a motor starter actually provides several layers of protection, and those protections are just as important as the starting itself.
Okay, so it's doing safety stuff in the background.
Exactly. Let's start with overload protection, because that's probably the most important one to understand.
Right.
An overload happens when a motor draws too much current over a period of time. That's usually because the motor is working too hard mechanically. Maybe a pump is jammed, a bearing is tight, or the load is heavier than expected.
So it's not like a short circuit.
Correct. Short circuits are sudden and violent. Overloads are slower, and the danger comes from heat building up in the windings.
And that's where overload relays come in.
Yes. Motor starters use thermal overload relays, electronic overloads, or thermal magnetic devices. They trip when the motor heats up beyond a safe level and disconnect the supply before damage occurs.
So overload protection is mainly for the motor itself.
Exactly right. That's a key exam point.
Okay.
Now, short circuit protection is different. This deals with very high current caused by faults like phase-to-phase or phase-to-earth shorts.
That's the fast-acting one.
Yes, short circuit protection is provided by fuses or circuit breakers installed upstream of the starter. They operate almost instantly to protect cables and equipment.
So overload relays don't handle short circuits.
Correct, they're too slow for that.
Got it.
Next is phase failure protection. If one phase is lost on a three-phase motor, the motor will overheat very quickly.
Even if it's still running?
Especially if it's still running. The currents become unbalanced, torque drops, and damage happens fast.
So how is that detected?
Some overload relays can sense phase imbalance and trip early. That gives protection against phase failure.
Okay, that makes sense.
Another important one is undervoltage or no-volt protection.
That's to stop the motor restarting on its own, right?
Exactly. If the supply fails, the contactor coil de-energizes and drops out. When the supply comes back, the motor won't restart unless the start button is pressed again.
That's a safety thing.
Yes, very much so. Unexpected restart can seriously injure people.
Yeah, I can see that.
And finally, isolation. Starters either include a manual isolator or are installed with one nearby. This allows safe maintenance and fault finding.
So everything can be fully disconnected.
Exactly.
That's a lot more protection than I realized.
Most people underestimate starters at first.
Okay.
Now, let's talk about phase reversal. If two phases are swapped, the motor runs in the opposite direction.
That could be bad for pumps.
Very bad. So phase reversal protection prevents the motor from starting if the phase sequence is wrong.
How does it do that?
Usually with a phase sequence relay. It monitors the order of the three phases, and if the sequence is incorrect, it prevents the contactor from energizing.
Sometimes it's done by wiring as well?
Yes, some systems use interlocked reversing contactors, so only one direction can be selected at a time.
Okay.
Now, let's move on to direct online starters.
The simple ones.
Yes, a DOL starter connects the motor directly to full line voltage when the contactor closes.
So no reduction at all.
Correct. That means high starting current, typically 5 to 8 times full load current.
That's pretty big.
It is. The advantages are that the design is simple, reliable, low cost, and easy to maintain, with strong starting torque.
And the downsides?
Very high starting current, mechanical shock, voltage dips on weak supplies, and it's not suitable for large motors.
So mostly small motors.
Yes, fans, small pumps, workshop machines, small compressors.
Okay.
Now, for larger motors, reduced voltage starting is often required.
Because the starting current would be too high?
Exactly. High starting current can cause voltage dips, stress couplings, trip protection, and even breach supply rules.
So we reduce voltage during start.
Yes,
That brings us to star-delta starters.
correct. During start, the motor is connected in star. Each winding receives a lower voltage, so starting current and torque are reduced.
Then it switches to delta.
Yes, after the motor accelerates, a timer switches the windings to delta, giving full voltage and full torque.
Advantages?
lower starting current, and fairly simple equipment. Disadvantages are reduced starting torque and a current surge during changeover.
So only good for light load starts.
Exactly.
What about auto transformer starters?
They use a tapped auto transformer to supply reduced voltage during start. After acceleration, the motor is switched to full line voltage.
Better torque than star delta?
Yes, with lower starting current, but they're more expensive and bulkier.
Used on big motors.
Yes, compressors and crushers, for example.
And primary resistance starters?
Those insert resistors in series with each phase during start. They reduce voltage but waste energy as heat.
So not very efficient.
Correct. They're rarely used today, mostly in older installations.
And electronic starters?
Also called soft starters. They use semiconductor devices to gradually increase voltage.
So very smooth starting.
Exactly. They reduce mechanical stress and electrical disturbance, and the start parameters can be adjusted.
Any disadvantages?
Cost and some harmonic distortion.
Where are they commonly used?
Pumps, conveyors, HVAC systems, and modern industrial motors.
Okay, I think I'm starting to see the whole picture now.
Good. Motor starters protect the motor, control starting current, and improve safety and reliability.
I'll definitely need to listen to this again.
That's perfectly normal. This topic builds over time.
Thanks, Mark.
Okay, Sarah. Before we finish, let's just quietly pull it all together.
Yeah, that would help.
So, three-phase motors use a rotating magnetic field to turn the rotor. They're strong, efficient, and that's why we see them everywhere in industry.
Right, much more than in houses.
Exactly. And because they're powerful, they need proper starters, not just to start them, but to protect them.
Like overloads, phase failure, and all that.
Yes. Overload protection looks after the motor windings. Short circuit protection looks after the cables and equipment. Phase failure and phase reversal protection stop serious damage before it happens.
That part makes more sense now.
Good. We also looked at different starting methods. DOL starters are simple but draw a very high starting current. Star delta, auto transformer, and resistance starters reduce that current in different ways. And modern electronic starters give smooth, controlled starting.
So choosing the starter really depends on the motor and the load.
Exactly right. That's the big picture.
Okay, I feel like I understand why we do this now, not just what the parts are.
That's the goal. This topic isn't about memorizing lists, it's about understanding how motors are started safely and reliably.
Thanks, Mark. I'll listen through this again later.
No worries at all. Take it slow, and we'll keep building on it next time.